You have been thinking for several months about forces, external forces, and how there are two kinds of forces, compression and tension, and how when you put a load on a beam, something happens to that beam. And if you have a big old sponge in your kitchen at home, you could actually demonstrate this in real life. So if you push down on that sponge like a beam, you'll notice that the holes in the sponge get close together at the top, the compression, and they get stretched out wider apart at the bottom, the tension. And we looked at that last term when we talked about trusses, I think. When you put a load on a beam, when you put a force on a beam, it causes a couple of things. It causes deflection, which is the distance that it moves down, but that's caused by bending. There are bending stresses in here, and those stresses have to be resisted by the material so that the thing doesn't come apart. The bending stress in this beam, the stress caused by bending, is a combination of compression in the top half. See the arrows pushing? They're pushing on each side. And tension on the bottom half. See those arrows? They're pulling away. So pushing towards, pulling away. And those beams have to deal with both compression and tension all at the same time without coming apart. Now, it's logical that if at the top of the beam, that beam is getting squished together and it's shorter, and at the bottom of the beam it's getting stretched out and it's longer, there must be some place near the middle of the beam where it's not getting shorter and it's not getting longer. And that place where it's not changing shape is called the neutral axis. You'll see engineering books talk about flexural stress, and that is just another name for bending stress. So flexure is bending, flexural stress is bending stress, and it is what happens in response to bending moment. Moment, force, here's a free body diagram, force times distance away from the pivot point. That's a moment. Here's a graph of some moment. And you might remember that last term we made some diagrams. We did a load diagram, a free body diagram, and under that we graphed the vertical shear that was happening in that beam. And under the shear diagram we graphed the bending moment that was happening in that beam. And when we made those graphs, especially when we looked at the bending moment, we noticed that the moment changed at different points in the beam, and the moment was biggest under where there was a load on that beam. Well, the flexural stress that that beam experiences is bigger when the bending moment is bigger. Makes total sense. When you put a load on a beam and it bends, where is that neutral axis? It turns out that the neutral axis goes right through the centroid. Whatever the cross-sectional shape of your beam is, it has a centroid, which you now know how to figure out, and that neutral axis is at the centroid. Our book here has drawn a beam that looks like a trapezoid, just to give us something unusual to think about. So its centroid would be here, and there's its neutral axis. You'll remember when we talked about modulus of elasticity, we looked at our stress-strain diagrams, we kept saying stress over strain, stress over strain. Hooke's law says stress is proportional to strain. All right, so looking down at a microscopic level, if that's true, then at the far far away from the neutral fiber as you can get, we have the maximum strain, the maximum stretchiness or shrinkiness. And that's illustrated by these arrows that he's drawn here. So a bigger arrow is bigger strain and bigger stress. A bigger arrow is bigger strain and bigger stress. So what he's illustrating is the farther away from the neutral axis you get, the greater the stress. And as you're bending this thing, the stress is compressive in the top as those fibers get shorter, and it's tensile in the bottom as those fibers get longer. And at the very top of the beam, you get the maximum compressive stress, longest arrows, and at the bottom of the beam, you get the maximum tensile stress, longer arrows. With greater stress, the farther away from the neutral axis we get. It turns out that this flexural stress, this bending stress, is much higher than just plain old tension and compression. This bending stress is what we are most concerned with when we're designing a structure and trying to make our beam or our column strong enough. Bending is the thing that governs. And when you look at the end view or the cross section of a beam or a column shape, you will notice that these shapes are designed so that they have the greatest amount of material out at the extreme fiber where the beam has the greatest stress. And isn't that interesting? Last time we looked at moment of inertia, and we looked at how you get a greater moment of inertia when you have material out away from that bending axis. Well, so that's how we design strong beams. We put flanges of one sort or the other out away from the neutral axis. Now I want to show you something interesting about marble buildings. As you might recall, concrete and stone are weak in tension. If you make a beam out of concrete and you don't put steel rebar in it, if it's just plain concrete, well, it's terrible in bending. It gets tension at the bottom, it cracks, and it falls down. This is why we use steel rebar in concrete. Well, stone is good in something that needs compression, such as a stone wall, or an arch, or a dome. Those are good for stone. Beams, not so much, because, as we've just been discussing, beams bend, and when they bend, they have tension at the bottom, and that is what stone is not good at. Okay, this takes us to the last 2 or 3 slides about Greek temples. You may be aware that in ancient Greece, Greece was covered with, it was forested. It was covered with big, I think they were cypress trees. And this was thousands of years ago. And Greece became deforested. And that was due not only to building buildings, but mostly to people cutting the trees to make charcoal to do metal smelting. They had learned how to do iron and copper and that sort of thing. And so they needed hot fires, so they cut down trees. Well, until Greece was deforested, they had used a post and beam architecture. Unlike the Romans, they never figured out how to do arches and domes. They knew how to do posts and beams, like this is an extreme example of. So they had a wooden architecture. When Greece was deforested, the builders looked around and said, uh-oh, what do we have to build with? Well, what they had to build with was marble. They had a lot of that. They had quarries they could quarry marble out of, not very many trees. And because they had not discovered arches or domes, they couldn't build Roman style arches, what they knew how to do was put up posts and put beams across them. So you can imagine maybe some trial and error happening. Cut the post out of marble. Cut the beam out of marble. Put it across the top. Uh-oh, marble's terrible in tension. It bends, it cracks, the thing falls down. And so gradually, over time, with trial and error, the Greek builders figured out how close together did they have to put those posts in order to keep the marble beams from bending and cracking. And it turned out it was about 8 feet. When you look at a Greek temple, it looks like they're farther apart, but they have put these capitals and these pads up on top of the columns so that they've spread out. It's like our snowshoe example at the start of the term. They've spread out the area wider so that the space between them is only about 8 feet. Well, what's interesting is that if you look at Greek temples, ancient Greek architecture, you will see not only do they use post and beam architecture, but they even duplicated the old wood building techniques in stone. So these things with 3 grooves cut in them, triglyphs they're called, those look like the ends of rafters used to look in wooden architecture. And underneath them, I don't know if you can see here, there are little cone-shaped things that look like the wooden pegs that were used to hold those rafters in place. So when you look at any of these ancient marble temples, when you look up close, you will see those 3 grooves, and under them those domes that represent pegs, and you will see this post and beam construction, but with the posts very close together, so as to avoid flexural stress, so as to avoid the beams falling down. And finally, here's an illustration that's labeled. Makes it a little bit easier to see. Finally, here is a replica of the Parthenon that was built in Nashville, Tennessee. I don't know if you've been to Nashville, but if you have, maybe you've seen this replica in their public park. It's an exact replica as far as we know, based on scholarship. It's full size, and if you look at the construction, you will see here are these triglyphs, and here are these cones, very clear to see. You will also notice that it's not white, by the way. So Greek temples, as an aside, have been, the remnants have been standing so long that all the coloring has been long worn away, and they've been bleached by the sun and they look white. But when they were first built, they were multicolored, they were quite colorful. And so the replica in Nashville has reproduced that. But our main point is thinking about flexural stress and how that affects how you can build with stone.